Hi, I'm Ramamoorthy. I'm from Sama Technologies. I'm a research engineer. I'm going to talk about anatomy of probabilistic programming languages. So yeah, I'm a research engineer at Sama. Sama works on clinical trial optimization using artificial intelligence. And what they do is they try to optimize the clinical trial pipeline using artificial intelligence so that they could bring the drugs to the market faster, thereby reducing the cost. So yeah, why study probabilistic programming? It's something that fascinated me. I started exploring Bayesian modeling a year ago, and I tried implementing Gaussian mixture models, Gaussian processes for hyperparameter optimization. I did all this in pytorch, and it was quite painful. There was so much boilerplate code. So yeah, and then I came across Pyro, Uber's Pyro, which is actually a low-level probabilistic programming language, in contrast to PyMC3, something like PyMC3, which is a high-level probabilistic framework. So yeah, when I was exploring Pyro, I came across this minimal implementation of Pyro called Mini Pyro, and it really fascinated me. The internals of Pyro fascinated me, so I studied it. So I wanted to share what I learned, right? So yeah, what is the objective of this talk? So basically, how do you build a probabilistic programming language with the minimum possible constructs, right? So yeah. By the way, why do we need to build probabilistic models? Why do we need probabilistic models? For uncertainty-aware modeling, for instead of loss hacking, every time we come up with a model, we need to come up with a loss function. We don't need to do that anymore. Like if you express a probabilistic model, the loss function kind of emerges organically from that, and the Bayesian framework has a natural way to incorporate prior knowledge into it. Objectives of this talk. So what do we want to do? We want to express any probabilistic model, and we want to do automatic inference to figure out the posterior or the unknown variables. And we would like to do predictions with uncertainty estimates. Okay, let's start with something really, really simple, simple linear regression model, something that everyone knows. So we have our data at table of values, and we define our parameters W and B, and our model is basically a linear combination of these parameters. This is as simple as it gets. So what does a learned model look like? This is what it looks like. It's a line fit based on mean square error objective. And as you can imagine, you could come up with a few more lines that fit the data just as good as this line, right? How do we arrive at those lines? Like, how do we make this model probabilistic? So what we could do is, instead of looking at weight and biases parameters, point estimates, instead we could look at them as random variables or distributions. Distributions from which we can sample from, and every sample corresponds to one line fit when the model is trained. The objective now is to learn these latent variables given the data. How does a learned model look like? What does the fit look like? This is what it looks like. This isn't a perfect estimate of the uncertainty, since our implementation of the inference algorithm is quite simplistic, a reduced version of the sophisticated variational inference algorithm. But you can see that the model accounts for all the data points, and the estimate of uncertainty seems reasonable. And now we know what we want. We move on to the important part of this session, automatic inference. What PPL offers is, it lets the users define the model, and and lets the user perform inference just by clicking a button, like one-click inference, by hiding all the details. So how do we get there? This is what we want, automatic inference. We have our data, we have a model that generates data. The model basically represents a joint distribution between observed and latent variables. And we have a guide. Guide represents a parametric distribution over latent variables. It basically defines the distribution over latent variables. Now the objective becomes learning the parameters of the guide. Right. So this is a high-level overview of our inference, automatic inference framework. SVI, stochastic variation inference. We'll look into variation inference and what it is. It's our general purpose inference engine in this case, and whatever model we throw at it, it should be able to figure out the latent variables. Right. And elbow, we'll look at the details of elbow. It is basically the universal loss function that I mentioned. SVI uses pytorch as optimizer to update the parameters of the guide, which basically what we want to learn, like to minimize the elbow objective. All right. So let's take a closer look at the model and guide, right? Okay, so as mentioned earlier, the model is given by a joint distribution between observed and latent variables. The guide is given by a parametric distribution. Here we call it a variational distribution with really nice properties. We consider two properties. One is that the variational distribution belongs to exponential family, which plays well with the logarithm, and it helps a lot in the math part. And the mean field assumption. So basically, if you take a closer look at the variational distribution in the figure, Q of Z, the Q distribution factorizes into Q of Z1, Q of Z2, dot, dot, dot. So that's what you call a mean field assumption, which also helps later. So in VI, we optimize the variational parameters given by pi. To minimize the KL divergence between the true posterior over the latent variables and our proposal, the variational distribution. So basically what we want to do is reduce the KL divergence. And it kind of, when it simplifies to a simpler form, elbow and evidence. Elbow is of the form given below in the bottom. And since the evidence is basically fixed, it's constant, increasing the elbow basically reduces the KL divergence. Now, let's take a closer look at elbow. Elbow, I didn't mention what elbow is, I will. Elbow is called the evidence lower bound. And the integral we saw here, basically what we do is we approximate it with the expectation. And the terms kind of simplify in this form. We have two terms. The first one is basically log of joint distribution, the model. The second term is the variational distribution. So yeah, if you look into it, we can calculate the log probabilities by sampling latent variables from Q. And we take the same samples and evaluate it under the model. And we sum up the log probabilities. We are able to sum up the log probabilities because of the mean field assumption. So the user writes model and guide as Python functions. And how do we track the latent variables in this case? For automatic inference, we need to track the latent variables. We design model and guide as stochastic functions that emit messages. For every parameter or a sample, we create a message and emit it. The param statement emits parameter messages, sample statement emits sample messages. Okay, so what do these messages look like? This is a parameter message. It has a name and it has a type, and it has a function which is basically set this value. and we give it an initial value in arguments, and the value is initially none. We can manipulate this value behind the scenes. So what happens, what we have to do with this message is basically maintain a global registry where we keep track of all the parameters, right? Okay, let's take a look at the sample message. Okay, so we consider one of our latent variables W, and the type of the message is sample, and a function associated with it is a normal distribution, a parameterized normal distribution, and doesn't have arguments, and the value is not yet set. Okay, so we have seen one part of automatic inference where basically our stochastic functions, the model and guide, will emit messages. And now it's our task to deal with these messages, how to handle them and actually do inference using them. So yeah, Pyro has this idea of effects and effect handlers. So far we have seen effects, so now we implement effect handlers. Trace is a really simple effect handler. All it does is it records all the messages. When it sees, it collects all the messages and keeps track of it. We have another handler named block. The block basically accepts a function as input, and basically, depending on a condition, it blocks some of the messages from the other handlers. The handlers are kind of organized as a stack. Anything below the block will not have access to the messages, the sample messages in this case. Okay. This is a bit more complicated. The replay handler. Why do we have this? Will make sense later. So we have what replay does is it runs trace on the guide and the model. First, it runs a trace on the guide and keeps track of all the messages. And when it's running the trace on the model, what it does is instead of instead of sampling from the distributions, from the latent variable distribution, it actually takes the values sampled in the guide trace, and then replaces it. As you can see in the figure, I hope it's clear. Yeah. Just to repeat, it runs a trace on the guide, then it runs a trace on the model, but the values of sample sites are set from the values from the guide trace. Now, why do we need something like this? Okay, so this is where it actually plays a role in calculating elbow. We have our model, we have our variational distribution. What happens here is we sample from the latent variables in the variational distribution and then evaluate it in both the model and the variational distribution. So this is exactly the scenario where we need a handler like trace. Right. This is an implementation of evidence lower bound using our handlers. We have already defined our guide and model. We run a trace on our guide, and we run a replay on our model based on the guide trace, and then we get a trace out of that. So what we do is we go through all the model trace values and evaluate it under the joint distribution, the model distribution. And we do the same in the guide trace. We go through all the values and we evaluate it under the Q distribution, the variational distribution. And we sum it all up, and that's basically our elbow, the evidence lower bound, which we need to minimize to arrive at our optimized solution. Okay. So now that we have implemented elbow, how do we implement SVI? So we have calculated the loss, so the difficult part is done. What we need to do in SVI is this. We just calculate loss and we keep track of parameters. Again, we use trace and block. We compose them together and build the loss values. So, once you calculate the loss, it becomes easy. So you just run a backward. You do a backprop and update the parameters, the variational parameters of the variational distribution, right? Yeah. So this is the example that we started with, Bayesian linear regression. We have a model and a guide, and we have an inference button. We have automated the inference procedure. Any other model, like, let's say logistic regression, what we do, we instead of just sampling from the normal distribution, we add a Bernoulli distribution on top or a multinomial distribution that will do our logistic regression. After training, how do we do prediction? We sample from the posterior predictive distribution, which is basically the distribution over the outcome variable. And we evaluate the outcome under the distribution for uncertainty measurement. And yeah, how do we do neural networks? We just compose distributions together instead of parameters, just like Legos, and we do the inference. Okay, that's pretty much it. It's way shorter than I imagined. So yeah, thank you.
Got some time for questions? No? Well, I have some. So I'm a big user of probabilistic programming languages as a statistician, and I've learned probably 5 of them over the years. How do you feel about the, I learned a lot about what's under the hood here today, because I never have cared. I want my inference button. What do you think about how the number of probabilistic programming frameworks out there? How can we best put that to use?
How do we best?
There's 5 big names.
How do we choose?
Yeah, how do we choose? What when it comes to a problem for you guys, for your work, what sort of things are you looking for in a probabilistic programming language? Or do you find yourself having to write a lot yourself?
Mm-hmm. So what I have experienced so far is people who solve very specific problems that could only be solved with probabilistic programming or Bayesian modeling. They go for something like PyMC3. And there is another part of the community that is focused on bringing probabilistic programming into deep learning. They look forward to Edward or Pyro. So yeah, there is that divide. I'm still exploring this. I'm more oriented towards Bayesian deep learning. We have our own issues. For example, variation inference that I mentioned, it doesn't scale very well. It's still an active area of research. So there are problems surrounding it. So yeah, I'm oriented towards that way.
Hi, I'm wondering if you have thoughts about how we should be doing things to encourage unification of APIs in the probabilistic programming land. So if this morning Matt Rocklin talked a little bit about how we need protocols and the likes, and we know PyMC has one of the most user-friendly APIs out there. So I'm wondering what we can do to bring friendlier APIs for probabilistic programming into and share that across PPLs.
I still feel like it's the probabilistic programming is kind of a niche area still. There isn't a large community surrounding it, right? So we have different small communities that work in different languages, but yes, we need a protocol that makes things easy for us. For example, I came across Eta-Limus. It's simulate backward, a new probabilistic programming framework that was published a few days ago. I saw it on Twitter. They have come up with a standard protocol, and they have built on top of it. There are a lot of similarities, between Pyro and that. So yeah, as people realize the importance of probabilistic programming moving forward, I'm sure they'll come up with more standard way to build newer frameworks.
Do you think maybe there's room for tooling for translating between different probabilistic programming languages? Like I know I've written the same model in Bugs, Jags, Stan, PyMC, PyMC3, all the same thing in all these different frameworks over the years. Do you think there's room for tooling to do that, or maybe the community could be better served by somebody coming together and documenting tips and tricks for how to do things like that?
Okay, I should be honest. I'm like completely out of depth here for related to this question.
That's okay.
I don't have experience with Stan or Jax. I'm not that old school. As I mentioned, I recently got started with it. I started with Pyro, so you should know where I'm leaning towards. So yeah, I don't think I should answer this question.
That's okay. I'm a very old person and I don't have an answer either.
Yeah.
Any more questions? All right, we're going to break for lunch until 2 p.m. Thanks to Suryadipan again for this wonderful talk, and thanks to all of our speakers this morning.